Welcome to the Dreamy Scientist, a quiet place in deep space with softly spoken science for sleepy minds. Tonight we drift through an alternative universe of where our Earth doesn't have a moon. So sit back, relax, and comment down below where in the world you are listening from and what time you are tuning in. It is always fascinating to know when and where you are watching from. If you enjoy these videos that I make, please leave a like and subscribe. If the moon had never formed, Earth would still be a blue world with continents, oceans, clouds, and weather. But the absence of a nearby massive satellite would quietly reshape many of the systems we take for granted. Tides, long-term climate stability, the length of our day, night brightness, eclipses, biological rhythms, and even how human cultures kept time. In this program, we'll examine those differences, one domain at a time, staying close to what's known from physics, geology, oceanography, and planetary science. Imagine Earth forming in the early solar system without ever acquiring a large natural satellite. The planet still accretes from rock and metal, its iron core segregates, its mantle convects. An atmosphere and global ocean emerge as volatiles Degas and cool. Orbital motion around the Sun proceeds as usual, governed by the same Newtonian dynamics. Days and seasons still exist because Earth spins and its axis is tilted relative to the plane of its orbit. What is missing is the persistent gravitational partner that, in our timeline, contributes torque on Earth's obliquity and injects energy into the tides. Remove that companion and several background processes run on different settings. Typical ocean tide ranges are smaller because only the sun drives them. Coastal mixing and estuarine flushing, which partly rely on tidal prisms, weaken in many geomorphic settings. Over geologic spans, the stabilizing influence of a large satellite on axial tilt is absent, so the envelope of possible obliquity states is wider, and the pacing of very long climate swings becomes less regular. None of that makes Earth unrecognizable. Winds still shape deserts, rivers still incise valleys, plate tectonics still rearranges continents. Human civilizations can still navigate, farm, and build cities. The change is that many boundary conditions that quietly steer life at the edges, shoreline ecology, sediment transport, calendar habits, and the deepest, slowest climate metronomes are tuned to a quieter key. The result is a planet that looks and feels like home, but keeps time, mixes water, and holds its axis with subtly different discipline. Differences that are small on the scale of a day and meaningful across eons. Tides arise because gravity varies with distance. The near side of Earth's oceans is pulled more strongly than the far side, and the water mass redistributes to follow equipotential surfaces while Earth rotates beneath this deformation. In our world, lunar forcing dominates at most coasts, and the Sun provides a secondary component. Their vector sum produces familiar spring and neap cycles. Without the moon, the solar tide remains, but the overall amplitude drops, often significantly, so many harbours experience lower highs and higher lows relative to today's mixed lunar-solar pattern. Local outcomes still depend on coastline geometry, shelf width, basin resonances, and weather. Narrow inlets can amplify even weak forcing, and storms can superimpose surges that dwarf astronomical tides. Still, the baseline is calmer. Currents driven by tidal range weaken, especially in funnel-shaped estuaries and across shallow banks where modern flows scour channels and maintain shoals. Internal tides generated where barotropic tides strike rough topography also diminish, reducing a pathway for vertical mixing in some parts of the ocean. For mariners, tide tables are simpler, fewer large excursions, modest daily variability, a greater emphasis on wind, pressure, and river discharge. For coasts, the practical effect is a quieter mechanical breath that alters sediment transport pathways, the exposure of mudflats and reefs, and the windows of opportunity for organisms that rely on robust fortnightly extremes. Intertidal ecosystems flourish wherever land meets sea, but their form is set by the magnitude and timing of inundation and the vigor of currents. In the moonless case, many shorelines inherit narrower vertical zones between typical low and high water because solar tides alone do the lifting. That narrows habitat bands for species adapted to periodic immersion, shifts competitive balances among barnacles, mussels, algae, and grasses, and reduces the export of larvae and detritus that, today, ride swift tidal pulses through inlets. Estuaries still mix salt and fresh water under the push of rivers and the drag of winds, yet with smaller tidal prisms, residence times lengthen and the pumping that ventilates channels becomes gentler. Morphodynamically, bars and shoals persist, but their turnover slows. Channel infilling and scour cycles dampen. Some delta distributaries that now rely on tidal energy to remain open become more sensitive to floods and wave climate. Salt marshes and mangroves survive and migrate with sea level as they do today, but their productivity shifts toward wind wave energy, storms, and riverborne nutrients as primary drivers. Over decades, these adjustments accumulate into different coastlines, still braided with creeks and lined by wetlands, yet sculpted by a milder oscillation and longer water residence. For fishers and planners, management tools tilt towards seasonal river flow, storm statistics, and stratification forecasts, while the familiar fortnightly rhythm recedes to the background. Earth's rotation slows because tides dissipate energy as frictional heat in the oceans and to a smaller degree in the solid Earth. In our timeline, the lunar component supplies most of this dissipation, lengthening the day by milliseconds per century and transferring angular momentum to the moon, which recedes. Remove the moon and that torque nearly vanishes. Solar tides remain, but are weaker. The practical implication is that Earth's day length still increases with time, just at a slower rate. On human scales, this is undetectable without precise instruments. Over millions of years, however, the integrated difference becomes visible in proxies. Laminated tidal rhythmites record different counts of daily layers per lunar month or per year. Growth bands in ancient organisms encode a slightly different beat between day and season. A faster average rotation persisting deeper into Earth history subtly influences atmospheric circulation by changing the Rossby deformation radius and the balance between inertial and pressure gradient forces. It also tweaks ocean basin resonances that depend on day length. None of these secondary effects overturn climate or habitability. They retune thresholds and patterns. For timekeeping, societies long ago decoupled civil seconds from Earth's irregular spin using atomic standards, so clocks stayed disciplined. But the astronomical day, the rotation of the planet relative to the Sun, marches toward modern values more slowly, and the story of how long a day is supposed to be is written on a gentler slope. Seasons arise because Earth's axis is tilted relative to its orbit, so sunlight shifts between hemispheres over a year. The amplitude of that tilt, obliquity, modulates seasonal contrast. In our reality, the moon's mass provides a stabilizing torque that keeps obliquity within a relatively narrow band over multi-million-year spans. In a moonless configuration, Numerical experiments show that gravitational interactions with the Sun and planets can drive larger excursions, allowing Earth to sample a wider set of tilt states across deep time. Greater obliquity means brighter polar summers and darker winters, favouring episodic melting and refreezing of high-latitude ice. Lower obliquity flattens seasonality, allowing snow to persist and influencing the growth of ice sheets by different mechanisms. Monsoon strength and position respond to these background settings, shifting precipitation belts and altering hydroclimate corridors. Greenhouse gases, continental positions, and ocean gateways still dominate the broad architecture of climate, but the metronome that paces extreme seasons is looser, and the spectrum of Milankovitch forcing, precession, obliquity, eccentricity recombines on altered periods. For paleoarchives, this yields different banding and phase relationships among proxies. For biogeography, it means migration routes and refugia move more often. The world is not chaotic day to day, yet the slow choreography of ice and heat plays with more improvisation than in a moon-stabilized system. Earth's spin axis precesses like a slowing top, drawing a circle on the celestial sphere over tens of thousands of years. Superimposed are nutations, smaller periodic nods, driven by gravitational torques. The Moon contributes significantly to both the rate of axial precession and the amplitudes of key nutation terms. Without it, the precession period lengthens and the nutation spectrum shifts, changing when solstices and equinoxes align with particular points of Earth's elliptical orbit. That timing matters because the intensity and distribution of sunlight at high latitudes, crucial for ice sheet mass balance, depends on these alignments. In paleoclimate, such shifts alter the phase and amplitude of ice age pacing relative to orbital parameters, producing different sequences of glacial advance and retreat even under similar greenhouse gas scenarios. For historical astronomy and navigation, the practical consequences are more modest but real. Star positions relative to the seasons drift on a different timetable, so the epochs used to tie catalogues to calendars adopt new constants. Surveyors, instrument makers, and almanac compilers still do their work. They just calibrate to a sky clock with slightly different tick spacing. The underlying lesson is straightforward. Change the torque budget on a rotating tilted planet, and the deepest calendars, the ones written in starlight and ice, advance in a subtly altered cadence. Total and annular solar eclipses rely on precise geometry. A physical moon must pass exactly between Earth and the Sun so that its umbra, the dark inner shadow, crosses Earth's surface, or when the moon is slightly farther away, so that the Sun becomes a bright ring in an annular event. Lunar eclipses, conversely, require the moon to enter Earth's shadow, painting the disk a coppered red as sunlight filters through our atmosphere. In a world where no large satellite ever formed, this choreography never occurs. The mechanical parts of the spectacle are missing. There is no orbiting body of the right size and distance to throw a shadow onto Earth or to receive ours. The consequences span science, culture, and human experience. Historically, eclipses motivated careful sky watching, calendar refinement, and eventually predictive mathematics that linked observation to celestial mechanics. They provided natural experiments, timing Bailey's beads, mapping the shadow's speed, and measuring the solar corona, whose ghostly streamers become visible only when the glaring solar disk is hidden. Remove eclipses, and a famous gateway into practical astronomy closes. Scientists still reach similar insights by other paths. planetary transits across the Sun, stellar occultations by asteroids, or spacecraft that block the Sun for coronal imaging. But the public's most dramatic lesson in orbital geometry vanishes. Culturally, stories, myths, and shared memories that hinge on midday darkness or a blood-red moon never enter the canon. Rituals and poetry follow different lights. Even logistics change at the margins. In our timeline, eclipse expeditions galvanized international collaboration and instrument development. In the moonless case, those bursts of cooperation coalesce around different sky events. None of this diminishes the grandeur of the heavens. Meteor showers still etch brief lines of fire, auroras still unfurl under geomagnetic storms, and bright planets still gather in striking conjunctions. But the singular moment when day briefly becomes dusk and a million people look up together would be a chapter unwritten, leaving the night sky simpler, quieter, and a little less theatrical. Moonlight is modest as physics, lunar albedo is low, and illumination at full moon is millions of times dimmer than sunlight, yet it transforms how night feels. A full moon turns snowfields silver, reveals shorelines in pale relief, and raises ambient light to levels that humans, livestock, and wildlife can use. Remove the moon, and average nocturnal brightness drops, especially in rural landscapes under clear, dry air. Before electrification, societies would have leaned more heavily on hearths, lanterns, and scheduled activity tied to dusk and dawn rather than to a repeating monthly cycle. Travelers plan by weather and familiarity rather than by bright nights. Fishing fleets time departures to tides, winds, and currents alone. Overland messengers, shepherds, and hunters rely on starlight and the faint wash of air glow, developing practices and routes that avoid hazards hidden in deeper dark. Wildlife adjusts as well. Many predators and prey modulate activity with lunar phase. Without that periodic signal, behaviors re-anchor to cloud cover, seasonal day length, and habitat structure. Pollinators that use moonlit cues shift to scent and temperature gradients. Human perception and art adapt. Painters and photographers develop a visual language of silhouettes, starfields, and reflected torchlight rather than the soft highlights and sharp lunar shadows familiar in our world. Urbanization eventually overwhelms natural patterns with artificial light, but the baseline is different. Where our ancestors sometimes worked or gathered under a generous full moon glow, their moonless counterparts operate under a uniformly darker ceiling, a constraint that shapes architecture, public safety, and social customs. Even crime statistics, which in our timeline sometimes correlate weakly with lunar brightness due to visibility, would follow other rhythms, driven more by weather, crowding, and opportunity. The night remains navigable and meaningful. It simply becomes a steadier, deeper shade, encouraging cultures to invent more of their own light or to embrace darkness as an organizing principle rather than an interlude between brighter nights. Along coasts, many organisms run on lunar time. Corals synchronize mass spawning near predictable phases. Certain fishes ride the largest spring tides to lay eggs on beaches. Invertebrates molt, feed, and disperse in step with fortnightly extremes. Take away the moon and the metronome changes. The sun still drives smaller tides. Winds, river pulses, and seasonal temperature changes still set strong signals. Evolution repurposes these cues to restore synchrony because timing is fitness. Coral reefs, for example, might shift toward aligning reproduction with seasonal thermal thresholds, plus consistent twilight cues or currents that guarantee dispersal, building redundancy into signals so that gametes still meet and larvae still ride favourable flows. Intertidal species adjust their vertical ranges as the narrower solar tide redraws the immersion window. Some taxa that depend on wide exposure may decline locally, while others gain ground in calmer, more stable bands. Planktonic communities feel the change indirectly. Internal tides weaken in places, altering vertical mixing and nutrient injections into the euphotic zone. The daily solar cycle still drives diel vertical migration, so the great nightly ascent of zooplankton endures. Farther inland, most organisms are unaffected. Terrestrial plants track photoperiod and temperature, not moon phase. Migratory birds that use lunar cues in part recalibrate to stars, geomagnetic information, and winds. Humans managing fisheries, conservation zones, and coastal infrastructure pivot from fortnightly calendars to seasonal and meteorological frameworks. What is lost is not synchrony, but one source of synchrony. Ecosystems remain rhythmic, they just find different drummers. Over decades, these rewired clocks produce coastlines with familiar actors and altered choreography, recruitment pulses that cluster around storms and seasonal fronts instead of spring tides, predator-prey encounters that peak under cloudless, starry nights rather than moonlit ones, and intertidal communities stratified by tolerance to slower, steadier inundation rather than to dramatic twice-monthly excursions. The very word month encodes our satellite. Ancient peoples counted lunations to structure agriculture, festivals, and debts. In a moonless world, calendars anchor purely to the sun. Priests and astronomers mark solstices and equinoxes, track the lengthening and shortening of days, and derive stable year lengths from shadows, gnomons, and star risings. Weeks and market cycles arise from social choice rather than from convenient fractions of a lunation. Maritime cultures thrive regardless. Celestial navigation using stars and planets remains precise, supported by dead reckoning, coastal piloting, and in modern eras, radio beacons and satellites. However, an important historical method, lunar distance measurements to determine longitude, never develops. Navigators perfect alternative chronometric techniques earlier or lean more heavily on improved timekeepers and stellar solutions. Tide tables exist but are thinner. With smaller solar tides, pilots focus on winds, river discharge, and barometric pressure, which can dominate water level on synoptic timescales. Cultural expression shifts accordingly. Where our literature and art are rich with crescents, crescents recede. Venus at evening, the Pleiades in autumn, and the Milky Way's winter band become recurring symbols of passage and return. Festivals cluster around harvest and solstice thresholds. Eclipses, absent entirely, contribute no cycle to myth or prediction. Architecture and city planning reflect darker nights. Colonnades and streets favour lamp spacing, sight lines, and reflective surfaces that maximise safety and wayfinding under starlight. None of this reduces human ingenuity or cohesion. Societies still coordinate sowing and reaping, pilgrimages and markets, voyages and wars. They simply do so against a solar scaffold of seasons rather than a monthly drumbeat, and their shared metaphors of time owe more to the sun's angle and the stars' positions than to a changing grey disk that never came to be. At planetary scale, ocean circulation is powered by winds, buoyancy fluxes from heating, cooling, and fresh water, and the Coriolis effect from Earth's rotation. These engines remain intact without a moon. What changes is the background tidal energy injected into the system, especially at boundaries where barotropic tides meet rough topography and convert to internal waves. In our timeline, internal tides propagate for hundreds of kilometers, and by breaking, contribute to vertical mixing that helps set the stratification profile of the ocean. With smaller astronomical tides, this pathway weakens in many basins. Fewer energetic beams radiate from continental slopes and mid-ocean ridges. Dissipation hotspots shrink, and the fine-scale turbulence that lifts nutrients into the sunlit layer declines in places where winds are not already dominant. Near coasts, reduced tidal ranges mean weaker exchange through inlets and sounds, lengthening residence times in lagoons and estuaries, and potentially increasing sensitivity to runoff and heat waves. Sediment transport across tidal flats and through channels slows, altering morphodynamics. Bars migrate more slowly. Shoals accrete or erode under a different balance of forces. Delta distributaries that depend on tidal scouring become more responsive to floods and storm surges. Fisheries experience these changes as gradual shifts in productivity and species composition along boundaries where small differences in mixing previously maintained sharp ecological fronts. On decadal horizons, management pivots toward forecasting stratification and wind events. On centennial scales, shoreline engineering contends with quieter but more persistent siltation problems. Globally, the overturning circulation, the great conveyor of heat and carbon, continues, governed by high-latitude buoyancy, forcing and winds, yet the texture of energy at the margins is smoother. The ocean is still lively, still structured, still capable of abrupt reorganizations under climate forcing, but one of its invisible hands is weaker, and the signatures of that weakness accumulate patiently at the edges where people live. Earth's surface is renewed and recycled by plate tectonics. Oceanic crust is created at mid-ocean ridges, dives at subduction zones, and thickens into mountain belts where continents collide. These motions draw power from internal heat, primordial energy left from accretion and segregation, and ongoing radiogenic decay, carried upward by mantle convection. Relative to that flux, tidal dissipation is small. Therefore, with or without a large satellite, volcanoes erupt, rifts open, slabs sink, and continents raft. The seismic catalogue still fills with intraplate flexure and plate boundary quakes. Hotspots still trail volcanic chains across moving plates. Supercontinents still assemble and fragment on half-billion-year cycles. Where the moon's absence intrudes is indirectly via surface boundary conditions that feed back on geologic processes. Reduced tidal ranges alter patterns of coastal sedimentation and estuarine infill, changing how much material rivers deliver to continental margins, and in turn, how wedges of sediment load foreland basins and trench systems. Long-term obliquity variability, freer to wander without lunar stabilization, modulates climate states that control erosion, glaciation, and sea level, all of which influence isostasy and the stress fields that nudge faults toward or away from failure. Yet these are second-order modulations. The deep engine cares little about whether a moon hangs overhead. For resource geology and hazards, the practical story is continuity. Ore bodies still concentrate where fluids flow. Hydrocarbons still accumulate where source, seal, and trap align. Volcanoes still demand respect. Earthquakes still require preparation. The rock record a billion years hence would read as recognizably Earth's. Basalt pillows at ancient ridges, accretionary prisms at old trenches, metamorphic cores of vanished mountains, its chapters ordered by familiar physics, its margins annotated by quieter tides, and a climate metronome set a touch looser than the one we know. When people picture the moon's role in Earth's safety, they often imagine a guardian, a large nearby body soaking up incoming debris so we don't have to. The truth is subtler. The inner solar system is populated by a spectrum of objects: dust, meteoroids, asteroids, dormant comets, whose paths are sculpted by the gravity of the sun and planets, by resonances in the asteroid belt, and by non-gravitational effects like the Yarkovsky drift that slowly shift small bodies' orbits as they re-radiate heat. Earth's sheer size and gravitational focusing make it the dominant target close to its orbit. Even with the moon present, most objects big enough to matter will either miss both worlds or be drawn toward Earth itself. The moon absolutely takes hits. We can read its history in crisp craters that never eroded away. So there are individual events where a fragment that might eventually have crossed Earth's path instead excavated a lunar basin. But statistically, the moon is not a comprehensive shield. Its cross-section is small compared to Earth's, and its presence can, in some cases, increase dynamical complexity. Lunar gravity very slightly perturbs passing fragments, altering encounter geometries in ways that are not uniformly protective. In a moonless configuration, Earth's impact flux would look broadly similar in order of magnitude. We would still experience a drizzle of micrometeoroids daily, occasional fireballs from meter-class bodies, rare but hazardous airbursts, and very rare crater-forming impacts over geological timescales. What would change is our record of those events. Without a handy, airless tape recorder hanging overhead, much of the inner solar system's cratering history remains hidden on Earth because plate tectonics and weather erase most scars. Science would rely more on Mercury, Mars, and asteroids to reconstruct bombardment epochs. Operationally, planetary defense priorities scarcely change. Telescopic surveys still map near-Earth objects. Radar still refines orbits, and deflection strategies remain indispensable. So the moon's protective role is real in specific instances, but modest in the aggregate. Its greatest shielding value for us has been educational, a nearby, well-lit archive of impacts that taught us the stakes, spurred crater science, and motivated the very monitoring networks that now watch the sky on Earth's behalf. The moon seeds a family of nighttime optical effects and observational conveniences that disappear entirely in a moonless world. Start with Earth shine. When the moon is a thin crescent, the rest of its disk glows dimly because sunlight reflects off Earth's bright clouds and oceans back onto the lunar night side. It's a quiet, elegant geometry lesson. Planet lighting moon that would have no analogue. Then consider halos and paraseleni, moondogs. Fine ice crystals in high clouds refract and reflect moonlight to produce a 22-degree ring, arcs, and mock moons. Without a lunar source, those familiar winter night displays vanish. We still get solar halos by day, but the night loses one of its most delicate ornaments. Moonbows, prismatic arcs formed by moonlight refracting through raindrops, also cease to exist. Waterfalls at night become purely dark dramas. Observationally, the moon is an unmatched occulter. Its limb skims stars, letting astronomers time occultations to refine star positions and historically to infer angular sizes. Absent a moon, we lose a bright, predictable, frequently available knife edge in the sky. We also lose lunar aureoles, soft diffraction glows revealing particle sizes in thin clouds, and the countless practical cues moonlight offers to naturalists and photographers assessing sky transparency at a glance. Maritime and aviation communities traditionally use the moon's phase and altitude to anticipate night brightness for navigation and training. In a moonless world, planning leans entirely on starlight, air glow, and anthropogenic light forecasts. Even language and metaphor shift. By the light of the moon, once in a blue moon, and cultural calendars pegged to first crescent sightings never arise. None of these absences breaks human life or science. We adapt with instruments, coronagraphs to study the solar corona, precise star trackers for navigation, sensitive photometers for sky clarity. Yet the cumulative effect is a quieter vault. Fewer serendipitous lessons written in ice and rain and diffraction. Fewer communal nights where a pale ring or a ghostly full disk in earthshine tugs eyes upward and silently teaches how light, crystals, and orbits conspire. In our timeline, the leading explanation for the moon's birth is a colossal early impact. A Mars-sized body struck the proto-Earth, ejecting material that coalesced into the moon while Earth's mantle remelted into a global magma ocean. Remove that event, or imagine an outcome in which debris never forms a long-lived satellite, and early Earth starting conditions likely differ in several respects, even if the planet's final mass and orbit are similar. Angular momentum is the first lever. Giant impacts can spin planets up or down and tilt their axes. Without a moon-forming collision, Earth's initial day length and obliquity distribution could skew differently. A shorter average day might persist deeper into Archean time before tidal braking slows the spin. Thermal history is the second lever. A global remelt promotes rapid core mantle chemical exchange, crustal overturn, and volatile loss or redistribution. In a no-moon story, the mantle may still be molten from accretional energy and other impacts, but the exact timing and vigor of crust formation and early tectonics could shift by millions of years. Volatile inventories also come into play. The canonical impact hypothesis allows both loss and later delivery of volatiles. Alternate accretion paths might leave Earth with slightly different surface water, carbon, and nitrogen budgets at key moments, affecting the pace of ocean formation, atmosphere composition, and the chemical playground where life begins. Even tides participate in the early script. With only the sun to drive them, near-shore mixing along newly formed coasts is weaker, which could modestly alter prebiotic concentration mechanisms that benefit from wet-dry cycling and periodic inundation. None of these differences implies a sterile Earth. Rather, the evolutionary corridor may bend. Timelines for crust stabilization, oxidation events, and the onset of plate tectonics could be re-timed. In practice, discerning such a counterfactual would require reading clues from other worlds, Mercury's and Mars's crustal records, asteroid families, exoplanet spins, to understand how often giant companions form and how strongly they reset a rocky planet's clock. What we can say is simple. Subtracting the moon edits the preface of Earth's story. Initial spin, early heat budget, volatile choreography, while leaving the main chapters of planetary physics intact. Before modern lighting, the moon was a working asset. Full moon nights opened markets, extended harvests, guided caravans, and set training schedules for militias and navies. Town charters and almanacs listed mooning nights when roads were safer and taverns busier. Watchmen and constables noted visibility as a factor in patrol patterns and deterrence. Remove the moon from history, and societies compensate in layered, practical ways. Architecture changes. Streets are laid narrower to keep facades within lamp range. Whitewash, polished stone, and reflective stucco become functional, not decorative, extending each lantern's reach. Settlements invest earlier and more heavily in public lighting. Oil lamps hung from cross streets, mirrored lanterns on key corners, later gas mantles and electrification, because there is no monthly boost. Rural logistics adapt their own rhythms. Threshing and haymaking stay tied to weather windows and manpower rather than to bright nights. Shepherds and drovers rely on fixed beacons and roadside hostels spaced by a day's walk. Maritime routines shift subtly. In our timeline, fleets often plan departures or coastal passages around predictable bright phases to ease navigation and signalling. Without that cue, seamanship leans more on tides, smaller but still relevant, winds, and the stars. Visual signalling at sea standardizes earlier on high-intensity lamps and flag codes that assume darkness is deep and frequent. Law and order follow suit. The faint statistical associations some cities have observed between moonlit nights and certain crimes vanish. Policing emphasizes crowd patterns, paydays, and weather instead. Night culture evolves a distinct etiquette. Escorts, lantern sharing, and the design of courtyards and arcades treat darkness as a default state rather than an alternating one. None of these adaptations is exotic. They are the ordinary ingenuity of communities optimizing for conditions. The broader point is that the moon's absence doesn't merely delete a poetic light. It removes a recurring logistical dividend, nudging societies to build more of their own illumination, to compress nocturnal activity into better lit districts, and to write bylaws, timetables, and architectural codes that assume every night is equally dark. Astronomy would flourish in a moonless world, but some classic ladders to the modern cosmos would look different. Historically, the moon served as a parallax benchmark. By measuring its apparent position against background stars from distant locations, early astronomers estimated distance, testing geometry, and refining Earth's size and shape. Later, lunar occultations, precise timings as the moon's limb-covered stars, sharpened star catalogues, and with careful analysis, even probed stellar diameters. Crucially for navigation, the lunar distance method used the angle between moon and a bright star to determine Greenwich time at sea, anchoring longitude before portable precision clocks were common. Without a moon, those pathways close. But alternatives exist and would rise earlier. Planetary transits of Venus and Mercury across the Sun can fix the astronomical unit via parallax. Systematic asteroid occultations can substitute for lunar ones in refining star positions. And improved chronometers push seafaring directly toward clock-based longitude rather than the intermediate lunar distance step. Solar physics also takes a different route. In our world, total solar eclipses exposed the corona and spurred understanding of the Sun's outer atmosphere. Absent eclipses, scientists rely more on coronagraphs, instruments that artificially block the solar disk, and on space-based platforms placed to avoid atmospheric scattering. The lack of a monthly bright object nudges observational culture too. Public star parties and education focus on planets, clusters, and the Milky Way. Amateur imaging emphasizes deep sky objects under uniformly dark conditions without a moonlit calendar to plan around. Space exploration retools its first test bed. We learned navigation, life support, and geology on the moon. In the moonless case, early robotic programs target Mars, near-Earth asteroids, or Phobos/Deimos as training grounds. The result is not a delayed science, but a re-sequenced one. Specific techniques and inspirational spectacles change, while the scientific method, measurement, prediction, revision, marches on. The cosmos remains legible. Its textbook just has a different opening chapter and a missing grey disc appendix that, in our timeline, made the sky feel close. Take away the moon and the nightly canvas shifts from a two-state system, dark and moonlit, to a steadier, deeper darkness punctuated by starlight, planets, and air glow. Human vision works differently across that range. Under bright conditions, the eye's cones provide colour and acuity. Under very low light, rods dominate, trading colour for sensitivity and pushing perception toward the cool end of the spectrum, the Purkinje shift. Moonlit scenes in our world often live in a mesopic middle where both systems contribute, yielding those iconic silver highlights and shadowed textures photographers and painters have chased for centuries. In a moonless world, mesopic nights are rarer outside cities. Landscapes lean towards silhouette and gradient, ridgelines against the Milky Way, water as a dark mirror, trees as layered cutouts. The arts respond. Painters develop a vocabulary of edge and negative space. Nocturnes emphasize star fields, luminous fog, fires, and windows rather than the glint on stone or snow. Poets and composers treat night as hush rather than as a second kind of daylight. Metaphors bend toward constellations and wandering planets. Architecture and lighting design evolve to honor the physiology. Towns shape sightlines to protect scotopic adaptation, shielded lamps, warmer color temperatures near thresholds, and courtyards that step down in brightness so eyes can migrate gently from interior to exterior. Cinematography invents its own solutions, where our directors can fake moonlight with large, cool sources to cue the audience. Their moonless counterparts standardize a different cue, perhaps a dim, warm, practical light in frame, or a consistent starlight grade that signals believable night without breaking immersion. Even personal technology follows suit. Lanterns and wayfinding tools favor beam patterns and intensities that respect dark adaptation, and fashion leans into reflective trims that read at low lux. None of this impoverishes the aesthetic, it transforms it. If our world's night is often a duet between sun-reflected light and shadow, the moonless night is a single instrument played with finesse, quieter, cooler, and profoundly spacious, inviting the eye to relearn how to see and creators to invent new grammars of darkness. In coastal societies, the practical calendar of food is written in tides, winds, light, and temperature. Remove the moon and the script is quietly redrafted. Fisheries first. Without strong lunar tides, many nearshore systems inherit smaller tidal ranges and weaker tidal currents, so the high-energy pulses that today ventilate estuaries, sweep larvae through inlets, and keep channels oxygenated are muted. Fishers adapt by keying their operations more tightly to seasonal wind regimes. River discharge pulses, baroclinic fronts, and the timing of storm passages. Set net placement, pot strings, and trawl tows shift toward corridors where wind-driven upwelling or bathymetric steering still concentrates forage. On the biology side, species that tune spawning to spring tides recalibrate around alternative cues, stable thermal thresholds, photoperiod, or recurrent current features, because synchrony is fitness. Eggs and larvae still need to meet transport windows that carry them to nursery grounds and back. Oyster, mussel, and seaweed aquaculture. Redesign sites for calmer oscillations. Long lines hang in deeper, steadier flows to avoid fouling and hypoxia. Hatchery release schedules leverage river pulses rather than lunar fortnightly peaks. Depuration tanks incorporate mechanical aeration to replace tidal flushing. At the margins of deltas and lagoons, residence times increase, so managers strengthen water quality safeguards. Bivalve closures respond to rainfall and temperature anomalies, not to spring neap cycles, and green infrastructure, constructed wetlands, setback marshes, becomes standard to intercept nutrients before they linger. Farther offshore, pelagic fleets feel less change. Diel vertical migration remains solar, mesoscale eddies still organize prey, and light lines at dawn/dusk continue to be productive. What alters is risk planning under a uniformly darker night. Deck lighting, watch schedules, and collision avoidance systems assume no monthly bright intervals, pushing a culture of consistent night discipline rather than alternating cautious daring phases. Agriculture, though largely solar, also bends to the new tempo. Pre-industrial communities historically aligned harvest festivals and night work, threshing, hauling, to bright full moons. In the moonless world, those tasks concentrate around market lamps, barn floors, and daytime logistics, driving earlier investments in rural lighting, grain storage, and communal labour exchanges. Irrigation gates, traditionally opened or closed to ride tidal heights in coastal paddies, are re-instrumented around river stage and barometric pressure, with smart controllers preventing salt intrusion during surges and maximising drainage before forecast rain. Salt making and seaweed drying are scheduled purely by weather windows and relative humidity, not by predictable spring low tides that expose flats. Salt marsh haying, still possible, rides late summer droughts instead of gleaming moonlit nights. Food safety frameworks adjust as well, with weaker tidal flushing in estuaries, baseline monitoring intensifies, and early warning networks. Fluorometers, oxygen probes, satellite colour, feed dashboards that guide closures and openings. The net effect is not a collapse of productivity, but a re-optimization. Fisheries and farms still thrive, yet their operating calendars shed a lunar metronome and embrace a matrix of solar and meteorological signals, supported by sensors, models, and social routines designed for a coast that breathes more quietly and a night that is consistently, honestly, dark. A moonless sky removes the simplest monthly lesson in celestial mechanics, the changing phases, and with it a sequence of classroom rituals that in our world begin with a cardboard disc and a lamp. Education responds by elevating other patterned phenomena to the front of the syllabus. Teachers lean on planetary motion, the synodic dance of Venus and Jupiter, the retrograde loops of Mars, and on seasonal geometry, why the sun climbs high in summer and skims low in winter, how day length changes with latitude, how equinox shadows trace straight lines on schoolyard meridians. Star parties centre on the Milky Way, clusters and nebulae, whose visibility is better on average without moonlight. Students map constellations across months to learn sidereal time and practice wayfinding by the sky's slow rotation. Where we would have used eclipses as a high-drama demonstration of alignment and scale, museums build coronagraph rooms and virtual reality theatres that simulate the solar corona, orbital nodes, and umbral geometry with data-driven fidelity, letting visitors walk along a synthetic shadow track even though nature never provides one. Navigation lessons swap lunar distance methods for a crisp narrative of chronometers, radio time signals, and GNSS, making longitude at sea a chronometry story from the beginning. Planetariums adopt transit days, Venus or Mercury crossing the solar disk, as community anchors alongside meteor showers and planetary oppositions. Outreach calendars advertise no moon nights, not as darkness warnings, but as opportunities to see the galaxy's structure and faint diffuse nebulae with the naked eye. Art and literature programs evolve in parallel. Without crescents as emblems, poets and painters turn to evening stars, the Pleiades, and the zodiacal light. Workshops teach how airglow paints horizons and how scotopic vision reframes colour, linking neuroscience to the arts. Safety and accessibility are foregrounded. Because every night is equally dark, amateur organisations standardise red light protocols, tactile star maps, audio-described sky tours, and quiet hours that protect dark adaptation, making public observing more inclusive. On the technology side, students learn to interrogate the sky with data. Light curve analysis of variable stars, minor planet occultations by asteroids, filling the role lunar occultations played for catalogue refinement, and citizen science campaigns that map light pollution with handheld photometers. The absence of a monthly sky clock also simplifies some messaging. Calendars can focus on solstices/equinoxes, on the analemma traced by the sun through the year, and on the geophysical consequences of tilt, precession, and eccentricity, tying astronomy to climate literacy without the detour through lunar timing. In short, the public still gets a coherent cosmos. It is learned through other doors, doors that may, in fact, open onto deeper vistas, because a consistently dark night makes the galaxy itself the teacher, and because educators respond with laboratories, instruments, and narratives that keep wonder intact while keeping the sky honest. Ports are only one edge case of lunar absence. The everyday plumbing of coasts must also be redesigned for smaller tides and longer residence times. Urban drainage illustrates the shift. In our world, storm drains, canals, and flap-gated outfalls exhale at low tide and inhale at high. With a gentler solar tide, the exhale is weaker and the timing less pronounced, so cities adopt smart outfalls with sensors and actuated valves that watch river stage, sea level, and pressure to prevent backflow during surges and to pre-drain basins whenever meteorology offers a window. Wastewater plants that once relied on tidal dilution during spring, ebb, install diffusers with active aeration, and they coordinate discharges to avoid stratified periods flagged by ocean colour satellites and in situ buoys. Coastal highways and rail lines, often built along historical marsh rims, face compound risk from rainfall, groundwater rise, and storm surge. Designers respond with permeable causeways, raised segments that let water and sediment pass underneath, and tidal channels restored through embankments to re-establish lateral exchange even when astronomical tides are small. Seawalls and revetments still exist, but the engineering imagination shifts toward living defences. Oyster reefs, mangrove belts, and broad foredunes that, in the absence of strong daily reworking, can be groomed to store sand and attenuate waves during the rare, large events that now dominate hazard statistics. Inlets and passes, no longer flushed by strong springs, are kept healthy with sediment bypassing systems and porous jetties that share flow rather than strangling it, while two-way fish passages are embedded in floodgates, so estuarine species can complete life cycles despite infrastructure. Power stations and desalination plants resite intakes in deeper, more oxygenated layers, and add variable depth skimmers to chase the best water during heat waves. Intakes are armoured with sacrificial aprons that resist slow siltation in the quieter mechanical climate. Tourism infrastructure adapts too. Beach access and lifeguard planning emphasise storm clusters rather than spring tides. Marinas use air bubblers and low-flow circulators to avoid stagnation. Night safety design assumes no moonlight, so boardwalk lighting is shielded and tuned to wildlife-friendly spectra while still delivering human-level wayfinding. Finally, governance adjusts, permitting moves away from rigid tide index standards toward performance-based criteria, oxygen budgets for basins, sediment continuity targets for littoral cells, maximum residence times for lagoons, monitored by dashboards that blend gauges, models, and citizen observations. The coastline remains a working edge, but its engineering palette is now more active, sensor-informed, and ecologically literate, supplying the mixing and exchange that the missing lunar pump once offered for free, and doing so in ways that make room for wetlands, fisheries, and neighbourhoods to share the same narrow strip between land and sea. Habitability is a system property, not a single lever, and Earth retains the essentials in a moonless timeline, a temperate orbit, a large ocean that stores heat and cycles water, a carbon silicate thermostat that draws down CO2 through weathering and returns it via volcanism, and a magnetic field that deflects solar wind. Remove the moon, and none of those core endowments vanish. What changes is pacing and variance. Without lunar torque, Earth's obliquity is freer to wander over multi-million-year intervals, sampling a wider range of tilt states that alter the contrast between summers and winters, especially at high latitudes. Ice sheets breathe on revised beats, advancing under some tilt combinations and retreating under others. Monsoons shift their footprints. Mid-latitude storm tracks follow sea surface temperature gradients that have been resculpted by a different mix of wind and tidal mixing. Meanwhile, the day length lingers shorter for longer because tidal braking is weaker. This subtly influences atmospheric circulation and the coupling between diurnal heating and planetary waves, while ocean basin resonances that depend on rotational speed evolve on a slower track. None of this implies fragility, it implies different corridors. Biodiversity patterns migrate along new climate isotherms. Refugia appear in alternate places as tilt oscillates. Evolutionary clocks tick to altered seasonality. Over geologic spans, solar brightening remains the inexorable amplifier, nudging climates. Warmer century by century regardless of moons, and the thermostat that regulates CO2 by weathering continues to counteract that trend on million-year timescales, as long as plate tectonics recycles carbon through subduction and degassing. The moon's absence does remove a convenient nearby laboratory where we learned early lessons in geology and exploration. It also reduces a stabilizing hand on tilt, but it does not erase the homemaking physics. Liquid water persists, continents continue to rearrange nutrient pathways, and the atmosphere maintains pressure and composition compatible with life. For human habitability, the engineering agenda focuses where it already must, mitigating greenhouse forcing, adapting coasts, and stewarding fresh water, because those levers dominate century-scale outcomes. In exoplanet science, the lesson generalizes. A large moon can steady obliquity and energize tides, but worlds without such companions can still be clement, especially if rotation, oceans, continents, and greenhouse gases conspire to share heat and maintain cycles. In sum, habitability is robust, yet the soundtrack is different. The same instruments, sun, rock, water, air, play a composition with fewer lunar percussion hits and more variability in the seasonal melody across deep time. A clear ledger helps. Lost are monthly phases, total and annular eclipses, strong lunar tides, earth shine, night halos, and moon dogs, the practical navigational method of lunar distance, and the cultural scaffolding built on crescents and full moons, festivals, idioms, paintings, and shared midnights bright enough to read by. Also reduced are certain conveniences in science, a nearby airless surface that archived the inner solar system's crater history, a readily available benchmark for parallax and occultation timing, a simple public gateway into orbital geometry. Remaining, however, are the fundamentals that make Earth Earth. Seasons from axial tilt, day and night from rotation, oceans and hydrologic cycles, plate tectonics renewing crust and regulating CO2, a magnetosphere, and skies still rich with planets, meteors, and the river of the Milky Way. Persisting too are tides, smaller, solar-forced ones that continue to breathe through coasts and stir estuaries, though with less authority. Synchrony in biology, which relocks to solar and meteorological cues. And navigation, which modernizes along clocks, stars, and radio rather than a grey disk. Some things improve. Consistently dark nights enlarge access to faint galaxies and nebulae. Certain measurements in geodesy simplify as lunar body tides vanish. Public stargazing gains more nights suited to deep sky viewing. Some things shift. Coastal engineering and water quality depend more on active design. Fisheries and aquaculture adopt meteorological calendars. Education pivots from monthly phases to planetary mechanics and climate literacy. And there are intangibles both ways. We lose a shared theatrical lesson in alignment when noon briefly turns to dusk, and we gain a cultural intimacy with stars and the Milky Way that is less often washed out by lunar glare. The net sensation is not absence so much as retuning. Human ingenuity fills gaps with instruments and standards. Ecosystems find new clocks. Cities re-illuminate themselves. Science builds alternative ladders to the same heights. The moon's presence in our timeline made some paths shorter and some metaphors inevitable. Its absence in this thought experiment lengthens a few routes and invites different stories, while the planet beneath those stories remains recognizable, workable, and capable of harboring meaning and life. Drawing the threads together, a moonless Earth is neither alien nor trivial. It is familiar physics arranged to a slightly different rhythm. The removal of a large companion subtracts tidal energy from the edges of the ocean and releases a stabilizing torque from Earth's spin axis. Those two edits propagate through coasts, calendars, and climate over vastly different timescales. Day to day, boats still depart at dawn. Farmers still read the sky. Cities still hum after sunset under their own lamps. Year to year, seasons still turn. Rivers still flood. Shorebirds still trace their long migrations along continents bound by gyres and wind. Century to century, societies adapt to compound flooding and heat with infrastructure that assumes quieter tides and uniformly dark nights, while science and policy focus on the same premier levers: greenhouse gases, land use, fresh water, because those dominate human experience more forcefully than any missing lunar phase. Across geologic time, the obliquity wanders more freely, adding variation to the choreography of ice and monsoon, while weaker tidal breaking lets shorter days persist longer. The biology of coasts rewires its clocks to solar and meteorological cues. Sediments settle in basins with a different patience. What disappears, eclipses, earthshine, a monthly lamp, matters to memory and method. What remains, sun, rock, water, air, and the deep rules that couple them, matters to home. If our world with a moon has felt like an orchestra with a steady percussionist, the moonless score is played pianissimo at the edges and rubato in the very long movements, yet it stays in tune. The practical moral is design, not lament, ports that mix themselves when tides will not, wetlands that absorb surges when strong springs no longer bleed them, curricula that teach orbital mechanics through planets and the climate through precession without the shortcut of phases, observatories that reveal corona with coronagraphs and the galaxy with consistently dark skies. The philosophical moral is humility. Habitability is overdetermined, and the moon was a generous teacher rather than a single keystone guarantor. In this quieter key, Earth is still Earth, workable, wondrous, and legible, inviting us to build wisely at the coast, to measure carefully in the dark, to keep faith with the long cycles we can influence, and to look up often at a sky where the Milky Way speaks a little louder because there is no monthly voice to interrupt it. In a world where the moon never formed, coastal engineering inherits shorelines that breathe more quietly, and that single difference propagates through nearly every design decision at the water's edge. Ports are laid out for smaller astronomical ranges, pilots rely less on fortnightly windows, and sediment management strategies confront slower but more persistent saltation because the tidal pump that today scours channels and exchanges lagoon water with the shelf becomes gentler. That has immediate implications for navigational depth because harbours that presently depend on robust ebb jets to move finds offshore would require either more frequent dredging or redesigned flow concentrators, training walls, spur groins, submerged sills that push modest solar tides to do focused work, while in estuaries the reduced prism translates into longer residence times, weaker estuarine turbidity maxima, and greater sensitivity to river and storm seiche. Planners therefore shift from spring neap calendars to meteorological ones, queuing maintenance to storm clusters and river pulse statistics, and they standardize adjustable infrastructure, movable sills, inflatable barriers, dual-purpose floodgates, so that the same hardware manages routine flushing in fair weather and surge exclusion in foul, because although everyday tides calm, compound flooding from rain, river, and storm surge remains a first-order hazard. Berth geometry also changes, since mooring forces see fewer high-frequency reversals from tidal currents, allowing longer quiescent windows for LNG transfer or container operations. But the flip side is greater reliance on wind wave climate and ship-induced currents to ventilate basins, so designers integrate porous breakwaters, baffle piers, and induced circulation jets to avoid dead zones and hypoxia. Tidal energy becomes a niche rather than a pillar in the coastal energy mix, pushing harbours to electrify with wind, wave, and solar, and to build microgrids hardened against salt, fog, and spray. In sediment-rich coasts, channel alignment and bend easing must assume that bars migrate more slowly, so life cycle costing emphasizes steady, modest dredge footprints over rare, heroic cuts and beneficial use programs that place dredged material to nourish marsh platforms become more predictable because the background tidal shear that can remobilize placed sediments is lower. Finally, operations culture evolves. Tide tables still matter, but pilots lean harder on wind, pressure, and river discharge predictors, VTS centers, vessel traffic services, fuse current profilers, and high-resolution nowcasts in lieu of simple harmonic predictions, and the human routines of harbour work, shift changes, tow windows, air draft clearances under bridges, are planned around a smoother sea-level envelope, yielding ports that feel familiar to our era, yet attuned to a quieter mechanical breath, where engineering must supply the mixing and scouring that the missing moon no longer provides. Smaller astronomical tides do not abolish coastal hazards, they reweight them, and that reweighting matters for risk models, building codes, and insurance portfolios. In the moonless case, the ordinary twice-daily rise and fall is milder, so nuisance flooding from high tides alone recedes. But compound flooding, the coincidence of storm surge, heavy rainfall, and elevated river discharge, gains relative importance because one of the timing knobs, spring neap modulation, disappears, and planners cannot count on exceptionally low tides to drain catchments between storms. Surge physics are unchanged. Wind stress piles water against coasts, pressure deficits lift sea surface height, and waves ride atop the surge. But with a smaller background tide, the perception of rare high waters becomes dominated by meteorology, which pushes civil protection to intensify forecast-informed operations, preemptive gate closures, movable flood walls, staged pump capacity, and to encode adaptive freeboard into design so assets remain safe as sea level rises. Inside estuaries and deltas, weaker tidal currents lengthen residence times and encourage backwater during river floods, so designers must prevent pluvial, rain-driven, and fluvial river waters from being trapped behind storm defences. This is where smart outfalls with check valves, gravity-forced switching, and distributed detention basins become standard, and where microtopography is restored to give water places to pause without hurting people. Tsunami risk is essentially unchanged in generation. Earthquakes, landslides, volcanic events. But the local modulation by tide is narrower, reducing the variance of first wave run-up while leaving the absolute hazard governed by source and bathymetry. The social layer matters too. Evacuation routes, siren audibility, and vertical refuge are easier to exercise when calendars are not distorted by neap week complacency followed by spring tide shock. But behavioural biases persist, so agencies adopt scenario libraries with immersive drills that couple realistic rain, surge, and river pulses to ensure communities can act under a deep, moonless night when electric light may fail and stars offer no useful illumination. In design practice, standards shift from tide plus storm addition with generous uncertainty to robust joint probability analysis that emphasizes co-occurrence and duration, and infrastructure such as subway portals, data centers, and hospitals move toward watertightness by default with redundant power sited above projected high water marks. Finally, back on the open coast, beach and dune management must contend with a gentler but more persistent baseline. Less daily reshaping by tide, more by storm clusters, so sand sharing systems, dunes, foredunes, berms, are groomed to survive long quiescent spells and then sacrificially surrender heightened sand during rare events, a rhythm written not by the missing moon but by the weather we still have. If lunar tides fade to a solar whisper, the tidal energy resource that in our world concentrates through straits and narrows becomes thinner, and that single constraint reorganizes coastal energy portfolios. Developers chase a few resonance-enhanced sites where solar tides and geometry still produce usable velocities, but the business case shifts decisively toward wave energy, offshore wind, floating PV, and hybrid systems that share cabling, substation platforms, and maintenance vessels to lower costs. In fjords and shelf edges, wave climate patterns remain driven by storm tracks and fetch, so arrays can be sited to complement wind farms temporarily. waves often peak when winds decline, and spectrally, devices tuned to different periods, with microgrid controllers smoothing output for ports that have electrified tugs, cranes, and cold ironing berths. Inside estuaries, reduced tidal currents change how much ventilation and oxygenation can be supplied passively. Historically, tide gates and culverts inhale and exhale with springs and neeps, so low head run of river turbines and aeration weirs appear not to harvest energy so much as to keep water quality in basins that otherwise stagnate under heat waves, a public health task dressed as infrastructure. Sediment dynamics also respond to the quieter mechanical climate. Siltation in intakes and around monopiles accrues slowly yet relentlessly, arguing for modular sacrificial aprons, frangible skewer mats, and sediment bypass pumps that run opportunistically when storms have enough surplus energy to move fines. On the policy side, planning frameworks that once carved out tidal priority zones now bake in multi-use sea space, with aquaculture sheltered in the lee of wind arrays and data cables threaded through corridors planned for maintenance vessel safety under uniformly dark nights. Economics adjust too, because in our timeline, some communities eye predictable tidal kilowatt hours as baseload-like, whereas here, predictability is supplied by diversity and storage. Gravity batteries in cliffs, thermal stores in district heating loops, and banks of Second Life EV packs housed in salt-misted bunkers. Interestingly, the disappearance of bright moonlit nights influences O&M logistics. Nighttime transfers favour higher intensity, shielded work lights, LiDAR-assisted docking, and strict dark adaptation protocols to prevent crew disorientation, pushing HSE rules to assume every night is equally black. In the end, the blue economy still thrives, but it does so by leaning into the energy that weather and swells freely deliver, while treating the missing lunar pump as a design fact rather than a lament, and by knitting energy, habitat enhancement, and water quality services into single seascapes that pay their way in electrons and resilience. Civilization can keep time without a moon, but the architecture of that time looks different from the ground up. The primordial human habit of counting lunations to parcel obligations and rituals never starts. So month as a unit of lived culture is replaced by solar constructs, fixed-length months by fiat, or flexible seasonal blocks keyed to solstices and equinoxes, codified early by priest astronomers who watch shadows crawl on temple meridians and note heliacal risings of bright stars. As states grow, standardization accelerates because trade and taxation strain under parochial calendars, and without the convenient teaching aid of phases, elite astronomers brand their authority by erecting gnomon farms and water clock networks to publish almanacs tied to the sun's declination, while seagoing powers double down on chronometry, pushing mechanical escapements, temperature-compensated balances, and later quartz and atomic clocks without ever detouring through lunar distance navigation. In science and engineering, the absence of a monthly astronomical beat frees metrology from calendar mythology earlier. Seconds and hours are decoupled from any insistence that 12 or 24 cleanly subdivide a lunar cycle, and by the time radio and GPS-like constellations appear, society is already fluent in ephemeris time, TAI, UTC, and the idea that Earth's rotation, UT1, is a wobbly customer corrected by leap seconds when needed. Law and labour feel the shift as well. Pay periods and tenancy terms anchor to fixed solar months, 28, 30 or 31 days by statute, or to 4-week blocks that simplify payroll, and religious calendars cohere around harvests and solstices rather than crescents sighted at dusk, avoiding, for better or worse, the sociological frictions that in our world arise when lunar months wander across seasons. The pedagogy of time follows suit. Children learn seasons from the sun's altitude and star maps instead of from a grey disk's changing face, and public outreach uses planetary conjunctions, equinox walks, and eclipse-free transit days to teach celestial mechanics. Even computing and data infrastructure inherit the divergence. Timestamp libraries never carry the month-length ambiguity that bedevils naive date math when lunations are involved, and scheduling systems in power markets, airlines and securities trades normalize on ISO-like week quarter frameworks with clean periodicities. Culturally, idioms drift. Once in a blue moon is meaningless, replaced by phrases tied to rare planetary alignments or long synodic intervals. Yet the core reality persists. Civil time is a human standard draped on astronomical bedrock, and in a moonless world, the drapery is simply more explicitly solar, more regular by design, and perhaps a little less romantic, while clocks, courts, and commerce tick with the same relentless utility we rely on today. High-precision positioning and Earth science would flourish with or without a lunar neighbour, but the models under the hood change in telling ways. Modern geodesy corrects for solid Earth tides, elastic deformations of the crust under the gravitational pull of moon and sun, as well as for ocean tide loading, polar motion, and nutation. Remove the moon and the largest of those tides drops away, leaving smaller solar tides to model and simplifying some loading terms along coasts where the ocean's tidal mass sloshes less vigorously, all of which feeds through to cleaner residuals in GNSS, GPS-like, data processing, and VLBI, very long baseline interferometry, solutions. Yet other complexities rise because the precession nutation spectrum shifts without lunar torque, which means reference frames like the ITRF and celestial frames like the ICRF evolve on different constants, and software that aligns satellites, ground stations, and star catalogues must be built on a reparameterized sky clock. Satellite altimetry benefits in one dimension. Tide corrections over the open ocean shrink, and the challenge of de-aliasing high-frequency barotropic response eases in mid-latitudes. But coastal altimetry still wrestles with waveforms corrupted by land returns, and with storm surge dominating extreme sea level, agencies put more effort into real-time pressure and wind fields than into elaborate tidal harmonic constituents. On land, engineers enjoy a small gift. With weaker ocean and body tides, long baseline strain meters, and INSAR satellite radar time series show less tidal breathing, making it marginally easier to isolate hydrologic loading, aquifer compaction, and slow slip on faults, though the sun still imposes a detectable signal. Navigation constellations themselves are deployed with the same orbital geometry: medium Earth orbits, ground track repeats, sidereal day resonances, but user equipment and augmentation networks may be simpler in their tide-aware corrections while being more demanding about dark operations, because field crews and reference station technicians cannot rely on moonlight during night maintenance, pushing safety protocols and lighting kits to assume perpetual scotopic conditions. In education, too, the narrative shifts. Instructors no longer demonstrate Earth tide by showing a GNSS antenna's height wobble with the moon overhead, but instead teach the concept with solar-only signatures and with satellite-to-satellite ranging that reveals Earth's elastic heartbeat under the sun alone. The net effect is not a loss of capability, but a remodeling of the mathematics and logistics beneath our most precise measurements of a breathing, rotating, wobbling planet, where the absence of one gravitational partner makes some equations cleaner, some clocks different, and the night work a shade darker. History shows that the Moon served as humanity's nearby laboratory for propulsion, life support, geology, and navigation. Subtract that laboratory and the architecture of early space exploration rearranges around different proving grounds, forcing both conservatism and creativity. The first orbital flights, spacewalks, and stations still happen in low Earth orbit, but when agencies look outward for a surface to touch, they choose near-Earth asteroids, Mars's moons, or small Mars polar landers as test beds because they offer accessible delta-V targets without deep gravity wells. Sample return missions go straight to carbonaceous asteroids to learn solar system chemistry, and the techniques we developed for lunar laser ranging are instead honed with satellite laser ranging and planetary radar, while the psychological and logistical exercises of multi-day surface sorties are practiced in Phobos/Deimos environments under microgravity, whose regolith, lighting, and communication delays teach lessons different from lunar days and nights. Absent a convenient, tidally locked body with 2 weekdays and nights, thermal design problems for surface systems show up at Mars first, where diurnal cycles are shorter, but dust adds complexity, and the cadence of human exploration likely stretches. Fewer flags and footprint sorties, more emphasis on robust orbital infrastructure, depots, and telerobotics that wring science from surfaces without always sending crews. Commercial space adapts as well. Sectors that in our world eye lunar polar volatiles pivot to asteroid resources and to cis-lunar-like depots placed at Earth-Sun Lagrange points, which still exist and still offer stable vantage for observatories and logistics hubs. Culturally, the absence of a looming grey disk narrows one powerful public symbol, but engineers and storytellers fill the gap with images of ring shadows on Saturn, plumes at Enceladus, and the blue limb of Earth seen from stations that grow larger, sooner, because they are the first, safest stepping stones. And while planetary protection, radiation shielding, and entry descent landing challenges do not change in physics, their sequencing does. Knowledge about dust toxicity, granular flow, and off-world field geology is built from Mars and small bodies rather than from lunar basalts and anorthosites, making the road to a multi-planetary civilization longer in calendar years, but arguably more systems-oriented, with deep supply chains, autonomous construction, and closed-loop life support matured before any grand push, so that when crews finally commit to Mars, they are backed by an orbital economy that grew strong without ever leaning on a nearby, forgiving neighbour that, in our timeline, taught us how to walk. Cities evolve a different relationship with darkness when there is no monthly pulse of moonlight to soften streets and yards. The starting condition is simple. Every clear night is equally dark, and from that, a distinct urban ecology, economy, and public health practice emerges. Street lighting is no longer a discretionary overlay tuned informally to bright and dim weeks. It becomes a primary infrastructure with the same design rigor as water or transit. Planners standardize shielded luminaires, lower correlated color temperatures to protect scotopic vision and melatonin production, and design lighting gradients, bright at intersections and crossings, gently tapering to residential levels, so that eyes adapt without glare or veiling luminance. Because there is no free ambient light, neighborhoods that in our world coast through full moon evenings must now actively choose visibility, and this choice exposes trade-offs. More light can raise perceived safety, yet degrade sleep, ecology, and the night sky. Less light conserves energy and biology, but demands better wayfinding and reflective materials. The moonless city therefore invests in non-luminous safety, high-contrast curb markings, retro-reflective crosswalks, prismatic paints on bollards, and building facades finished with micro-textures that return headlamp light without adding sky glow. Parks and waterfronts adopt dark corridor zoning where illumination is kept intentionally low for wildlife passage, bats, owls, migrating insects, while trails use low-mount bollards and motion-sensing task light that rises only when people are present. Public health agencies, freed from the small but measurable swings in night brightness that moonlight imparts, design sleep campaigns around fixed conditions. Blackout curtains become standard code in multifamily housing near bright corridors. Hospitals and care homes implement circadian respectful lighting schedules where night shifts work under warm, low-lux scenes and patients recover in rooms that actually get dark. Policing and community safety shift emphasis from brightness alone to visibility engineering. Sightlines trimmed, corner mirrors installed, and camera IR illuminators used sparingly and with privacy guardrails. Commerce adapts. Restaurants and venues cultivate night signatures that read well at low lux. Warm pools on tabletops, tight halos at entries, rather than blasting facades. Logistics yards switch to masked lights with precise optics that keep lumens on task and not in the sky. Ecologically, uniform darkness benefits many species. Hatchling turtles on distant beaches are still vulnerable to artificial glow, but are not periodically lured by full moon brightness inland. Insect mortality at lamps drops when spectra and output are tuned. Urban birds that miscue by light at night see steadier conditions that planners can actually control. Finally, cultural life leans into the rediscovered sky. With no lunar glare, the Milky Way becomes a reachable civic goal under dark sky ordinances. Astrotourism walks, rooftop observatories, and lights-out festivals make the night a shared public asset rather than a hazard to be banished. In short, a moonless metropolis does not simply add more lamps, it designs the night, balancing safety, sleep, stars, and species, because every evening starts from true darkness, and only deliberate choices steer what people see, how they rest, and which non-human neighbours can still afford to live beside them. If every night is equally dark, the operating assumptions baked into vehicles, robots, and infrastructure shift from opportunistic moonlit performance to reliable scotopic baselines. Autonomous cars, delivery bots, track inspection crawlers, and port equipment can no longer expect intermittent boosts in scene illumination. Instead, they must see, localize, and decide in darkness as a design constant. That pushes sensing suites towards sensor fusion with redundancy. Low-light CMOS or EMCCD cameras tuned for starlight levels. Active modalities such as eye-safe LiDAR with glare management to coexist with headlamps. Short and long-wave infrared for thermal contrast. Polarimetric channels that read skylight patterns at dusk and dawn. High dynamic range radar for weather penetration, and accurate inertial cores bridged by GNSS, visual odometry, and SLAM that are robust against feature-poor corridors. Because the sky offers no monthly lamp, infrastructure cooperates. Lane markings and signage use retro-reflective microprisms readable at ultra-low lux. depots embed visual fiducials and passive markers that pop under IR. Rail rights of way add passive RF, ID, or UWB beacons where occlusion is frequent. Maritime autonomy benefits similarly. Watchkeeping models trained on moonlit video in our world must be retrained on truly black horizons, where false positives, sky/sea confusion, and false negatives, unlit small craft, are mitigated by thermal sensors and AIS sanity checks. Aerial robotics and crewed aviation also recalibrate. Helicopter EMS and SAR flight rules standardize NVG, night vision goggle ops, and synthetic vision overlays as routine rather than surge capability during dark weeks. Small UAS shift to down-angled, shielded task lighting and thermal payloads for inspection without contributing to sky glow. Beyond visual line of sight corridors, incorporate reflective cues and acoustic beacons so that silent drones remain trackable by ground teams. In the built environment, smart lighting participates in autonomy. Machine-addressable luminaires can raise local levels for an approaching robot or emergency convoy, then fade, achieving safety without permanent brightness. Software engineering changes too. Datasets include moonless edge cases by default. Simulators inject realistic star fields, air glow, wet asphalt bloom, and human eye adaptation models so that HMI human-machine interfaces avoid blinding operators with sudden white UI flares. Safety doctrine evolves. Since there is no cyclical bright period to schedule risky work, organizations adopt always dark playbooks, standardized conspicuity garments, redundant personal beacons, and enforced dark adaptation protocols where appropriate. Finally, ethics and ecology gain weight in design. Active sensing must avoid mass insect attraction or wildlife disturbance. LiDAR and IR flooders are power managed and spectrally chosen to minimize non-target impacts. The result is not a fearful economy stalled by darkness, but a mature one where machines are native to night, built to perceive honestly dim scenes, coordinated by infrastructure that speaks their language, and governed by standards that assume the moon will never show up to help. Farming has always been a solar art dressed with local lore. Remove the moon and the agrarian calendar sheds a familiar ornament without losing its backbone. Most crop physiology responds to photoperiod and temperature sums, rainfall timing, soil moisture, and wind. Thus sowing, flowering, and harvest remain legible. Where lunar effects have been noted, nighttime illumination affecting some insect navigation, predator-prey encounter rates near full moon, or modest correlations with animal behavior. Their removal clarifies signals and forces management to pivot toward controllable levers. In integrated pest management, for instance, the absence of moonlit nights reduces alternating cycles of predation visibility. Nocturnal predators such as bats and owls hunt under consistently dark conditions, potentially stabilizing suppression of certain moths and beetles that otherwise alter flight under bright moons. Conversely, some pest species that historically curtailed movement on bright nights may fly more steadily, redistributing risk. Traps and pheromone lures are deployed with weather-based scheduling, temperature thresholds, wind minima, and humidity, rather than lunar calendars. In irrigated deltas and coastal paddies, smaller tides change sluice operation and salinity control. Smart gates now time opens to river stage and pressure, and farmers rely on soil EC sensors rather than spring-low windows to flush fields. Livestock management, often tied to body clocks and human labour availability, adapts with lighting strategies that respect circadian biology. Since there is no periodic full moon intrusion into barn windows, lighting programs for dairy yield and animal welfare become more uniform and easier to standardize. Post-harvest logistics shift night work from full moon bonus hours to electrified yards and refrigerated cross-docks designed for safe, low-glare operation. Rural roads are marked and reflectively dressed because there is no natural fallback. On the phenology side, extension agents and growers build decision tools that lean heavily on degree day models, soil moisture indices, and canopy stress sensing from drones and satellites. Advisory bulletins lose the lunar column and gain high-resolution weather nowcasts that predict heat spikes and VPD vapor pressure deficit events, which move yield more than any missing phase. Pollination ecology alters subtly. Some moth-pollinated plants that open under dim conditions find a world that is always dim. Garden and hedgerow strategies shift to support diverse nocturnal pollinators with habitat and spectral appropriate farm lighting. Aquaculture at the land-sea interface retools around aeration and circulation rather than tidal exchange. Inland recirculating systems benefit from the predictability. The cultural calendar of farms adapts too. Harvest festivals anchor to equinox, not moonrise. Workshare co-ops publish solar fixed schedules, and agricultural education drops lunar lore in favour of climate risk literacy, heat-tolerant varietals, water use efficiency, and soil carbon. Netting it out, the moonless countryside is not mystically altered. It is operationally clarified. Seasons still write the music. Farmers simply conduct with instruments they can control, while pests, predators, and pollinators negotiate a night that never swings brighter and never needs to be second-guessed by phase. Beyond coasts and fields, many inland species quietly reference the moon as illumination, as a compass cue low on the horizon, or as a timing correlate layered onto temperature and day length. Strip that lamp from the sky and orientation stacks rebalance. Night-migrating birds, for example, already steer by star patterns, geomagnetic cues, and polarized skylight at twilight. The loss of lunar azimuth as a redundant reference barely dents their toolkit, while the gain, fewer bright nights that tempt attraction to artificially lit urban cores, may help if cities adopt dark sky codes. Amphibians leaving ponds and salamanders crossing roads do so under steady darkness. Road ecology programs respond with reflective edging, illuminated culvert mouths that leak just enough task light to cue safe passages, and seasonal closures triggered by soil temperature and rainfall rather than bright night alerts. Bats, whose activity sometimes dips on bright nights due to predation risk, may show more consistent foraging with cascading effects on insect populations. Conservationists rebuild roost corridors with spectrally friendly lamp choices and hedgerow networks that provide echolocation structure without adding glare. Large carnivores and their prey settle into more stable night-day partitioning, where moonlight once modulated hunting success, vegetation, terrain, and human disturbance become the dominant controls. Aquatic systems inland, reservoirs, rivers, lakes, see little direct lunar effect beyond subtleties in fish behaviour. Diel vertical migration in zooplankton remains solar, and riparian restoration focuses on shade, temperature, and flow. Fireflies provide a poignant case. Their bioluminescent dialogues sometimes compete with moonlight and artificial glow. The absence of a lunar competitor makes lighting policy even more decisive. Warm, low output, motion-sensing garden lights protect courtship. while blue-rich continuous illumination erases it. Predator-prey acoustics in forests, owls versus rodents, lose one variable, illumination swings, and refocus on habitat structure. Managers thin with an eye to soundscapes and visibility at animal eye level rather than to lunar calendars. Recreational culture adjusts as well. Hikers and cyclists accustomed to full moon outings evolve starlight routes with reflective blazes. Park agencies expand night permits guided by wildlife-sensitive lighting and quiet hours enforcement because every night is equally inviting for human eyes and equally disruptive if unmanaged. Scientific monitoring takes advantage of the uniform baseline. Camera trap studies no longer dereplicate by phase. Acoustic arrays, thermal drones, and passive light sensors paint cleaner time series in which weather and anthropogenic light are the major confounders. Ultimately, inland ecology gains predictability. A constant night allows conservation to treat darkness as habitat, engineered, zoned, and measured, so that orientation, movement, and life history events rest on cues biology actually evolved to read, not on a monthly light that can be mimicked or mangled by street lamps. Operational communities, first responders, maritime patrols, border services, defence forces, plan around visibility more than romance. Remove the moon and the baseline becomes permanent low-light operations. Doctrine shifts from opportunistic scheduling to capability hardening. For police and EMS, that means vehicle lighting with adaptive optics that illuminate scenes without splashing windows, standard issue personal beacons, and IR strobes that interoperate with aircraft and drones, and training that normalizes night navigation on foot using retro-reflective waypoints and thermal imagers. Fire services redesign wildland tactics. The familiar moon-assisted glow that can aid nighttime burnout operations vanishes, so crews lean on thermal drone overwatch and fire-resistant lighting that won't attract insects or blind operators. Search and rescue gains from consistent darkness. NVG and thermal proficiency become universal. Ground teams deploy passive markers that guide helicopter hoists. Lost person behavior models are recalibrated for hikers who never planned full moon hikes because those nights never exist, shifting prevention messaging to weather and preparedness rather than to lunar calendars. Maritime security and navies standardize dark ship detection under thermal and radar, while small craft collisions are mitigated by stricter light and AIS rules. Boarding teams train to read wakes and silhouettes in a sky that offers no glare band along the horizon. Military forces rewrite night fighting assumptions. Where some doctrines historically exploited bright moons for fast movement, the moonless playbook emphasizes sensors, discipline, and emissions control all the time. Thermal camouflage, laser safety, LPI/LPD, low probability of intercept/detection, communications, and blue force tracking that does not rely on periodic bright nights for visual deconfliction. Urban conflict introduces lighting as terrain. Forces shape neighborhoods with selective illumination to deny or grant visibility while protecting civilian circadian health. Counter-UAS defense must function under starlight, integrating acoustic, radar, and EOIR-infused timelines. Cyber-physical risk intersects here. Because lighting is networked to cooperate with autonomy and public safety, it becomes a target. Resilience demands fail-secure modes that drop to safe presets rather than to darkness or uncontrolled glare. Finally, humanitarian operations and disaster relief adapt logistics to a night that never brightens. Field hospitals, water points and shelters are laid out with reflective grids and low-glare mast lights. Convoy SOPs mandate convoyable light signatures that balance visibility and protection, and public information campaigns teach households to keep dark-adapted kits, headlamps with red/amber filters, retro-reflective tags, and window coverings that keep neighbourhoods coordinated without lighting the sky. The strategic constant is humility before physics. In a moonless world, everyone is a night operator, and the organisations that prosper treat darkness as a designed environment with doctrine, tools, and ethics to match. Take away the moon and you do not remove complexity, you reassign it. From a celestial partner that once did free work at the coasts and in the calendar to institutions that must coordinate deliberately. International standards bodies write the grammar of a moonless age, lighting codes that limit blue emissions and sky glow. IHO/IMO guidance that assumes smaller tides but larger compound flood risks. IEC/ISO protocols for machine-readable luminaires. So emergency convoys, robots and transit fleets can request temporary lights safely. GNSS augmentation standards that embed solar-only Earth orientation parameters. Science agencies build shared observatories. Coronagraph constellations replace eclipse expeditions. Global tide and mixing arrays quantify how much energy the oceans lost without lunar forcing. Open bathymetry and sediment transport models help ports with quieter tidal prisms manage silt fairly. Conservation accords extend night to habitat. Dark sky reserves migrate from boutique parks to metropolitan regions with enforceable caps on lumens per capita and spectra by land use. Flyway treaties fold in artificial light management as a peer threat alongside habitat loss and climate change. Education ministries harmonise sky literacy. Students graduate able to read solstices, star clocks, and the Milky Way, replacing the intuitive monthly lesson of phases with curricula that connect orbital mechanics to climate resilience. Finance aligns incentives. Catastrophe models pivot to joint probability flood metrics. Resilience bonds reward cities that retrofit drainage and living shorelines to replace the missing tidal pump. Utilities price night tariffs that reflect the true cost of lighting under permanent darkness, nudging adoption of shielded, efficient fixtures. In space policy, exploration architectures become collaborative by necessity. No lunar playground means shared deep space test beds, pooled depots at Earth-Sun Lagrange points, and common safety rules for thermal and dust operations at Mars and small bodies. Ethically, the night itself gains standing. Right-to-dark frameworks emerge alongside right-to-light, balancing safety with sleep, wildlife, and culture. Public health tracks melatonin and sleep debt as seriously as noise and air quality. The research agenda follows the edits the moon's absence imposed. Long horizon climate dynamics under freer obliquity. Coastal water quality under slower exchange. Insect and pollinator networks under spectrum-managed nights. Automation safety and fairness when night is the default. And equity in illumination, ensuring dark sky protections do not become a luxury while some communities bear glare and sleep loss. The through line is cooperative design. Where a companion once steadied tilt and stirred seas, societies must steady and stir by policy, engineering, and shared norms. Done well, the payoff is twofold. Cities sleep better and see the galaxy again. Coasts breathe by living infrastructure. Science advances with instruments that do not wait for rare celestial alignments. The quiet sky is not an absence, It is an invitation to coordinate, to treat darkness, coastal exchange, and timekeeping as common goods maintained by common effort. Good night.